Okay, so our third example is analytical geometry. So application of the maxima and minima in analytical geometry. So find the point on the curve y is equal to x squared, which is closest to the point 3, 0. Okay, so if we try to graph that, so y is equal to x squared, that is a parabola opening, since this is x squared, so this is parabola opening to the opening upwards. Okay, so it's opening upwards, so therefore it should look like this. So if this is x and this is y, so the curve should look like this. So it's a parabola opening upwards. Okay, so if we have this one as our point 3, 0, okay, so its y coordinate is 0, so therefore it lies along the x-axis, so it's 3, 0. So let's say this is our curve, our point 3, 0. Okay, so then its shortest distance would probably be at this point. Okay, so so it can have many distances. Okay, so depending on the point of the point along the parabola, so it could be this distance, okay, or this distance. Okay, so but we are looking for the shortest distance. Okay, so what is the shortest distance? So let's say this is our point xy. Okay, so that is our point. We are looking for that point. Okay, and then again, this curve is y is equal to x squared. So this is the relationship between x and y. So between these 2 points, x and y, so this is their relationship. So we are trying to look for the shortest distance. Okay, so therefore we are minimizing the distance. And if you recall the distance formula, okay, from analytical geometry, so distance between 2 points, okay, so d is equal to square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, okay, so where x1 and y1 are the coordinates of the first point, and x2, y2 are the coordinates of the second point. Okay, so let's say this is our first point. Okay, and then this is our second point. So therefore the objective function that we are trying to minimize is d is equal to square root of x2, so coordinate of the second point is x, minus x1, so the x coordinate of the first point, so x minus 3, okay, squared, plus y2, so y coordinate of the second point, minus y coordinate of the first point, 0. Okay, so that is our objective function, and then we are trying to minimize the value of d. Okay, so as you can see, our objective function is expressed in terms of two variables, x and y. So therefore we must first express the objective function in terms of one variable only. Okay, so by expressing y in terms of x or x in terms of y using this relationship. Okay, so this is the relationship between x and y. Okay, so it's easier, I think, to replace y with x. Okay, but you can also replace x, okay, with y. So from here, if we have y is equal to x squared, then x is equal to square root of y. Okay, you can insert here x is equal to square root of y. But I think that would be more difficult since we have a radical. Okay, and then you will expand that radical, square root of x minus 3, square root of y minus 3 squared, so that would be difficult. So it's easier for us to replace y with x squared. So d is equal to square root of x minus 3, sorry, this is squared, x minus 3 squared plus y now will become x squared. Okay, so we can expand, okay, the expressions inside the radical sign. So d is equal to square root of, so this will become x squared minus x times 3 times 2, so that's minus 6x, and then plus 3 squared, that is 9, and then plus x squared squared, so that's x to the power of 4. Okay, or we can rearrange this and then express the radical in exponential form so that we can derive it easier. So it will become x to the 4th plus x squared minus 6x plus 9 raised to 1/2. Okay, so this is now our objective function. So we will set its first derivative to 0. So set the derivative of d with respect to x to 0. So deriving first, so the derivative of d with respect to x is equal to, so deriving this, so we will be using the general power formula, so where this whole expression is our u and then this is our n. Okay, so by the general power formula, this will be 1/2 times x to the 4th plus x squared minus 6x plus 9 raised to 1/2 minus 1 multiplied by the derivative of this. So the derivative of this is derivative of x to the 4th is 4x cubed plus 2x minus 6x plus minus derivative of 6x is negative 6, derivative of constant 9 is 0. Okay, so simplifying, so the derivative of d with respect to x is equal to, so this now will become, will go to the denominator because this will be raised to negative 1/2. 1/2 minus 1 is negative 1/2. So therefore, this will now become, so this is in the numerator, so 4x cubed plus 2x minus 6 over 2, and then x to the 4th plus x squared minus 6x, okay, plus 9 raised to 1/2. Okay, so since we set the derivative to 0, so therefore this whole expression is equal to 0. Okay, so now, so to solve for x, so what we can do is we can cross multiply the denominator. Okay, cross multiply to 0, and if we cross multiply this denominator to 0, so what will remain is only the numerator. So what will remain is 4x cubed plus 2x minus 6 is equal to 0. Okay, so as you can see, we also have a greatest common factor of 2, so we can factor out 2, and then what will remain is 2x cubed plus x minus 3 is equal to 0. So dividing both sides by 2 will also eliminate the numerical coefficient, so therefore what will remain is 2x cubed plus x minus 3 is equal to 0. So now let us find the roots of x. Okay, so we will solve for x. So since we have here a cubic, so we can try using the can try using the synthetic division, okay, and we can also use the remainder theorem, okay, to estimate what the value of x would be. Okay, so by synthetic division, so we have writing the coefficients of the expression. So we have 2, then x squared, we have 0, x we have 1, and then constant -3. Okay, so we will assign a number, okay, so as value for our x. So let's say x is equal to, so by remainder theorem, if we check here, if we substitute x is equal to 1, okay, so if we substitute x is equal to 1, then this will become 0, right? So by remainder, sorry, okay, so at x is equal to 1, so then this will become 2 times 1 cube plus 1 minus 3, okay, so that is equal to 0. So therefore x is equal to 1 or x minus 1 is a factor. Okay, so but for factoring purposes, so let's use synthetic division. So if we have 1 there, so let us divide. So 2, bring down 2 times 1, that is 1, add 0 plus 1, that is 1, 1 times 1, oh sorry, 2 times 1, that is 2, okay, and then 0 plus 2, this is also 2, and then 2 times 1, that is 2, and then we have 1 plus 2, we have 3, 3 times 1, that is 3, and then this will become 0. So therefore factoring, so 2x cubed plus x minus 3, sorry, is equal to 0. So one of its factors is x is equal to 1 or x minus 1. Okay, and then this will be the coefficients of the remaining factor. So starting with x squared, x, and constant. So 2x squared plus 2x plus 3 is equal to 0. Okay, so next we can factor this further to find all the roots. So 2x squared plus 2x plus 3. So let's multiply 2 times 3, that is 6. So factor 6 such that the sum of the factors is positive 2. So 6 only has one factor, 2 factors, that is 1 times 6 or 1 times 6, or it could also be 2 times 3. Okay, so none of the factors will sum up to the coefficient of the second term. Okay, so therefore this term cannot be factored out further. Okay, so therefore we only have one root, x minus 1 is equal to 0, or x is equal to okay, x is equal to 1, sorry. Okay, so so therefore that is the x coordinate, okay, of the minimum, sorry, that is the x coordinate of the point of minimum distance. Okay, so we can try using the second derivative, okay, to test if that's really a minimum. So but I think there is no need to solve to prove that it's a minimum point, because we only have one root. Okay, so we are trying to solve if it's maximum or minimum, and since we have only one, okay, so that most probably will be the minimum point, okay, without testing for the second derivative. But if you really insist, if you really want, so you can also try to solve the second derivative. So from here, so get the second derivative and then substitute x is equal to 1. So if it's greater than 0, then this is the minimum point. Okay, so therefore, at x is equal to 1, solving for the y coordinate, so since we have y is equal to x squared, so we have 1 squared, so that is equal to 1. So therefore, minimum distance to 30 is at 1, 1. Okay, so that's it. Okay, so for our final example, so maxima and minima can also be applied in economical design. Okay, so when we say economical design, so it will give us the best design in terms of cost of constructing uh, um, geometric figures. Okay, so say for example, so we have here an open cylindrical tank of volume 192 pi cubic feet is to be constructed. So if the material for the sides costs $3 per square foot and the material for the bottom costs $9 per square foot, find the radius and the height of the tank which will be most economical. Okay, so for this problem we are asked to construct an open cylindrical tank. So meaning it's a cylindrical tank for which the top is open. Okay, so it's an open top cylindrical tank. So let's say, so given, so let's say our tank looks like this. Okay, so it's open at the top. So we are asked to find the radius and the height. So let's say this is our height, h, and then our radius, of course, from the center. So this is our radius. Okay, so we are given that the volume is equal to 192 pi cubic feet. Okay, and we are also given the costs, okay, of the materials. So for the sides, so the lateral surface, so here, okay, so this whole surface, so its cost is $3 per square foot. Okay, and at the bottom, so the bottom material, so let's have projection line there. So the bottom, so it costs $9 per square foot. Okay, so we are required to solve for the radius and the height of the tank, okay, which will be most economical. So when we say most economical, it will give us the least cost of constructing the tank. Okay, so our required is the radius and the height, okay, for which the cost is minimum. Okay, So we are minimizing the cost here. So for our solution, so obviously our objective function will be in terms of cost. Okay, so we will construct a function, okay, of the cost. Okay, so if we let C as our cost, okay, so our C now will be equal to, so the total cost will be the materials, total cost of the materials used for the sides plus the total cost of the materials for the bottom. Okay, so cost of sides plus the cost at the bottom. Okay, so the cost now, oh sorry, this is 9 cubic, 9 square feet. So the cost now, okay, as you can see, is per square foot. Okay, so $3 per square foot for the sides and $9 per square foot at the bottom. So therefore, we will be needing the area of the lateral sides and the area at the bottom. Okay, so since this is a circular cylinder, okay, so the area at the bottom will be equal to the area of a circle. Okay, so the area of a circle given radius r is pi r squared. Okay, so for the sides, so for the area of the sides, so it will be the lateral surface area of a cylinder. So if you recall the formula, so the area for the side, okay, for the lateral surface area of a cylinder, it's equal to the circumference of the circle multiplied by the height. Okay, so the circumference is 2 pi r, okay, multiplied by height. So therefore it's 2 pi r h. Okay, so therefore the cost for the sides is equal to the price multiplied by the area, and the cost of the bottom is equal to the price multiplied by the area at the bottom. Okay, so therefore our cost function is equal to, so price is 3 multiplied by the area at the sides, 2 pi rh plus the cost of constructing the bottom material is its price, which is $9 per square foot, multiplied by its area. So it's 9 times pi r squared. Okay, so if you simplify, so this will be equal to, so 2 times 3, that is 6 pi r h plus 9 pi r squared. Okay, so as you can see, we have already established the function of the cost. So as we can see here, it's the cost is a function of the radius r and the height. Okay, so we need to express it first in terms of a single variable only. Okay, so we need to replace r with h or h with r. Okay, but how do we get the relationship of h and r? Okay, the height and the radius. So yes, very good. So you need to use this volume. Okay, so the volume of a cylinder, if you recall your geometry, so that's pi r squared h. So the volume is equal to the area multiplied by area at the bottom multiplied by the height. Okay, so since volume is equal to pi r squared h, and it's also equal to 192 pi. Okay, so we can, for the left and the right side, so we have a common coefficient of pi, so we can cancel that out. And then for this, I think it will be easier if we express h in terms of r, and then use that h to replace the h in our cost function. Okay, so because if we use r squared, then it will involve radicals, so our function will be a little bit complicated. So we just use h, so dividing both sides with r squared. Okay, so cancel, r squared will be cancelled, so therefore h is equal to 192 over r squared. Okay, so therefore our cost function will now become 6 pi r multiplied by h, replacing h with 192 over r squared, plus 9 pi r squared. Okay, so as you can see, we can cancel out 1 r, so therefore our cost function in terms of one variable only, which is r, is equal to, so 6 times 192, so we have 6 times 192, so we have 1152, so 1152 pi over r plus 9 pi r squared. Okay, so next, to minimize our c, or our cost, so we need to derive it with respect to r. Okay, so we need to derive it with respect to r. So setting derivative of c with respect to r is equal to 0. So deriving this, so the derivative of c with respect to r is equal to, so we have here a coefficient of 1152 pi, so we can write it first. So 1152 pi multiplied by, so the derivative of 1 over r, so the derivative of 1 over r, so since that is r raised to negative 1, okay, or you can also write it as 1152 pi r raised to negative 1 plus 9 pi r squared. Okay, so deriving that, so we will have negative 1 multiplied by r, so negative r raised to negative 1 minus 1, so that is negative 2. Okay, plus, so deriving this, so 9 pi, write 9 pi, the numerical coefficient, multiplied by the derivative of r squared, so that is 2r. Okay, so setting that to 0, so we can rewrite this as negative 1152 pi over r squared, okay, plus we have here 18 pi, okay, is equal to 0. Okay, so this is the derivative, and then equating it to 0. So the next thing that we're gonna do is we will be solving for r. So but at the same time, let us eliminate pi, and also if 1152 and 18 has a greatest common factor, so let's also simplify that. So that's 1152 over 18. Yes, it's a perfect multiple, So therefore, we can multiply both sides of the equation by r squared over 18 pi. So multiplying this with r squared over 18 pi. On the other side, multiply it also with r squared over 18 pi. Okay. So multiplying this, for the first term, it will eliminate r squared, and then what will remain is eliminate r squared. We will also divide negative 1152 pi divided by 18 pi. So that will become, from earlier, it's 16. So it's negative, it's not 16, it's 64. So negative 64 plus, so you multiply, if you distribute this on the second term, so it will become 18 pi will be cancelled, and then it will become r squared, okay, is equal to 0. So transposing 64 on the other side, so we'll have r squared is equal to 64. Okay, taking the square root of both sides, so r now will become, since we took a square root, so r now will become positive or negative 8. Okay, so but since this is a geometric problem, so a negative dimension will be what do you call this? It will be insensible. It's absurd. So therefore, so take only r is equal to 8. So its unit is consistent with our unit. So since we are using cubic feet and square feet, so our r must also be in foot. Okay. So since we have our r already, then from here, so h is equal to 192 over r squared. So therefore, our h is 192 over r squared. So that's 192 over 8 squared. Divided by 8 squared. Our height is only 3 feet. Okay, so therefore, for our answer, r is equal to 8 feet. And then our h is equal to 3 feet. So this will give the lowest price, okay, in constructing the the lowest cost, okay, in constructing the cylindrical tank. Okay, so to sum it up, so basically you have to be very proficient with the formulas, okay, of areas, lateral surface areas. So some problems you will also encounter volume of different geometric figures. Okay, so you have to be review all of those formulas. Okay, so that's it for this video, and see you on the next lessons.